Hello, welcome to Notes on Solving Trigonometric Equations. That's a big word for me. All right, so we are solving. This is going to be the one and only video for solving trig equations. So if it's 20 minutes long, that's what it's going to be. It should be shorter though for honors because there's an advanced section that you won't be responsible for. When we are solving anything, the goal is always to isolate the variable. So we can always have that in the back of our heads if we are ever stuck on anything with these trig equations, because what we'll find out is the difficult part is going to be the algebra behind this. And I'm currently working on an algebra kind of helper for you guys that I hope to disseminate, that I hope to get out to you guys for the purpose of helping with these trig equations and such. So with this first example, we are going to isolate our x's. Now we first see our x's are inside these sine functions. So sine of x on the left and sine of x on the right do need to be collected on one side of the equation. And what I like to do when I'm solving is to try and get all my terms positive. It doesn't look like we'll be able to do that though. So I'm going to try though, and I'm going to add this negative sign over to the left side. So I'll get sine of x plus sine x plus radical 2 equals 0. And one thing you'll notice, I think number 1 is the exception here. We'll see how much space it takes me, but I'm always going to work down. If I have to work across, it would be to start a new line and then work down again. So we'll see if we can fit all that work in here. So I see two sines added together. So if you are ever stuck, and I'll use this strategy later as well, if you are stuck, pretend that sine is like a y variable. So we have two y variables added together. That would make two sines, right? So we can use that little, we can use old algebra rules with these trig functions. So I have two sines here, plus radical 2 equals 0. So I'm still trying to isolate x. Thankfully, I've combined these two like terms, the sine functions, and I only have one x to deal with now. So now I have to get to this x, and then I have to go through my radical 2 that's being added to this 2 sine x. So I'm going to move that to the other side of the equation. Sorry, my nose is really stuffed up. I've been sneezing like crazy. And if I keep on moving, I see the 2 multiplied by sine, and I want to divide both sides by 2, so I'll end up with negative radical 2 over 2. Okay, so this is looking familiar now. We have sine of x equals negative radical 2 over 2. If you are answering these questions, excuse me, we are going to always answer in radians. So we're answering these trig equations with radians, and maybe you want to make a note to yourself there if that's going to be a hard thing to remember. But we're always answering in radians. So if you're using a calculator, you could use inverse sine. So take the inverse sine of negative radical 2 over 2. If you're not using a calculator, you're using the unit circle, which is my preferred method. It's something you should be comfortable with. So we want to know which angles satisfy this equation. So what angle gives us a sine of negative radical 2 over 2? Now, the first one that I can think of happens in the third quadrant. So that's 5 pi over 4. I've got another one that I know of that happens in the fourth quadrant, and that's 7 pi over 4. And you might be like, but wait, there's more. There definitely are more. Because this next statement here is a general solution to a trig equation should be represented as an infinite amount of angles, because 5 pi over 4 and 7 pi over 4 are just two of the angles that make this equation true. We know that there are more because we know that there are an infinite amount of coterminal angles to 5 pi over 4 and 7 pi over 4. So if we just look at their locations in the first and second quadrant, or sorry, third and fourth quadrant, I draw a poor unit circle right here. We know we can rotate around a full circle. So we can rotate a full circle more and get another angle that satisfies this equation. So we can add on 2 pi to both of these. But not only that, we could keep on adding 2 pi so that, you know, we would go around the circle another time, and then we find another coterminal angle, and we keep on going, keep on going. So we introduce this this letter here, n, and we've seen this before, that acts as a counter for a multiplier for how many revolutions or how many circles that we take to get to another solution on for this equation. So you might have realized also we can definitely subtract a rotation from these, so we can get negative angles that are also satisfying this equation. So what we've found here, these are our general solutions that produce an infinite amount of solutions. I'll abbreviate that right there. So that's our general solution. And you can tell that it's a general solution because it has that plus or minus 2 pi in there. Cool. So that lays the groundwork pretty well for us. We're going to try and do 4 more examples if you're in honors, or sorry, 3 more examples if you're in honors, and then 1 more example if you're in advanced. So let's dig into it. If you don't have your unit circle with you, it's going to be super important for you to have that. So if you want to pull it up, then you'll be ready. Again, I apologize for my nose just dripping. Okay, this second example. So the second example has a pretty nasty trig like term on the left, and it seems like we have to do the same thing we did in the first problem and try and isolate from there. There are some algebra skills that are critical to completing this one, and I'm going to do my best to remind you guys what they are along the way. And most of the time, that's all you need is just a reminder. You all have the ability to do this. It's just maybe you forgot, or maybe you just can't see it right now. So what I see in this problem is a I've put my cotangents on one side of the equation, but what I also see is this cotangent x and this cotangent x are in two separate terms. So I don't want to have two of them, right? I would like to just have one. So if you have, let's say you have like, and you don't have to write this, let's say you have like a times b minus 2a equals 0. How can you get only one a from that? You would factor that a away. And that's very simple looking. But because there are so many letters just jam-packed in here, this looks like it's impossible to factor, but it's really not. So we're going to actually factor cotangent x because it's shared between each of the terms. And then we have this nice result equals 0. So cotangent x times cosine squared x minus 2. This might not look nice to you guys, but this is actually a really good thing. Whenever we have multiplication between two things equals 0, we know that one of these things, this is the 0 property, so we know that one of these things has to equal 0. In fact, either of them could be 0, so we have to split up this multiplication problem into two separate equations. And you've done this before with quadratics. You did it all the time. That's how you solve quadratics. So you're now solving just these two separate equations with that 0 product property. So if I'm going to solve cotangent x for 0, I've got to go look on my unit circle. I can do that. And we will do that, but there's a little bit more I've got to do for this other equation. What I'm going to do first is I'll go ahead and solve cotangent x equals 0, and then we'll start on the second one there. Cotangent x equals 0 when cosine is 0. So that is true when x is equal to pi over 2 and 3 pi over 2. So we have two different locations on the unit circle where that is true. When we are finding when it says solve, we are finding the general solution for this, and I want to, directions will be made clear in the practice on what you're to use, find the general solution, for example. But we want the general solution, and if we are finding the general solution for a cotangent function, remember from Miss White's video that tangent and cotangent have different periods. They cycle quicker than sine and cosine, meaning they complete revolution. They complete their pattern faster than cosine and sine do. So cotangent's period is not, I wouldn't add on 2 pi n, I would just add on pi n, because pi is the period of tangent and cotangent. So you can see that it's actually redundant for us to have both of these here, because the one of them will cycle to the other. For example, they're pi apart in their in these two solutions. So we only need one of them. So we don't need to write this one, even though it's correct. Yeah, I'll leave it there though. For this other side of the equation, we are going to be setting cosine squared x equal to 2, and then cosine of x, we're going to take the square root plus or minus the square root of both sides. So we'll get plus or minus radical 2. So what we're looking at for cosine of x equals plus or minus radical 2 is really strange, because radical 2, if you put that in your calculator, that's a number that's bigger than 1. So on this side of the equation, remember that cosine its ratio only exists between -1 and 1. And you can remember the graph for that of the parent function. So there's actually not an angle that gives us a ratio of radical 2. So there's no solution on that side of the equation. So if we're going to write a solution for this entire equation, we would just pick one of those cotangent general solutions that we found. All right, so example 3. Example 3 has a quadratic type setup for this trig equation. What I'm hoping you notice is this is a trinomial, meaning it has 3 terms, 1, 2, 3, but it is a quadratic trinomial, meaning one of its terms is squared, and that's this first one. So we have, if we can think about this with variables, which it might help you, and this is okay, if we can say that y equals sine x, then rewriting my equation looks like this: 2 times y squared minus y minus 1 equals 0. So now I have a quadratic that I need to solve. And if I solve that, I'm going to have 2 factors, 2 binomials. So I have 2y plus 1 and y minus 1 as my 2 factors, and then the set equal to 0. So this looks really weird right now, but if we can put, like, it's not what we were doing before, but if we can put our sine of x back into this, so if we can re-substitute, should probably write that, re-substitute. Sine x for y, then we'll get 2 sine x plus 1, and then sine x minus 1 equals 0. So our problem is now back to a trig problem, and this is all right for me to do as long as I've defined my variable as sine of x. I'm allowed to do this, and I'm just double checking to make sure that I didn't do something silly. Yeah, I think we're good. Yes, we are good. So now that I've got this all ready to go, I can use that zero product property that we talked about, and I can say that 2 sine x plus 1 equals 0, and that's one of my factors equal to 0, and sine of x minus 1 equals 0. So sine of x equals 1 for that one, and sine of x equals, and I'll do the subtraction and multiplication, or sorry, the subtraction and division in one step. So I'll get -1 divided by 2. All right, so this is actually not so bad at this point. Like I was saying, the trig might be the easiest thing to do for this, because this is just looking at the unit circle. So where are these angles? Where do they exist? And our angles for the left side, or the left factor there, are going to be 7 pi over 6. My brain's working, trust me. A plus or minus the period of sine times n, so 2 pi n. And then we have, so that's the, what quadrant is that? That's the third quadrant answer, and now we have a fourth quadrant answer, because sine is negative in these two quadrants, the third and fourth quadrants. And so we need our 11 pi over 6. And I'm just barely fitting it in there. Okay. Got it. Plus or minus 2 pi n. Great, so that's one side of the equation. And the other side is when sine is equal to 1. So that's when our y value on the unit circle is 1. So x is equal to, and that's actually only one spot. That's at pi over 2 plus or minus 2 pi n. Right, so there are a lot of solutions here. They are all, we're not picking and choosing from them. They're all different. So we need to have them all as our solution set. Now, I believe at this time we're well into 20 minutes. So if you are if you're interested in example 4, then stick around until after I talk about these interval solutions, which I kind of crossed through there. But if you just want to see example 4 done, it's very similar to number 3. Then stick around. And if you're in honors, then thanks for watching. You can also see the 4th example at the end of the video, but I'm going to jump into interval solutions for advanced right now. Let me get rid of this strike through. So interval solutions here are for advanced because they're just asking you to do a little bit more. When we're looking for interval solutions, it's because we want to know some specific solutions that happen in just one cycle of the domain of these functions, typically between 0 and 2 pi. So we want to know the interval solution to examples 1 through 4 on the interval 0 to 2 pi. So if we're looking at this solution to number 1, we already have these two solutions. It's kind of simple because we already have the general solution. We can use the general solution to generate these interval solutions as well. So if we are looking for the interval solution, then we have a list of angles. So 5 pi over 4 and 7 pi over 4. Now I know if I added 2 pi to these two angles, then I would be outside the range of 0 to 2 pi. So those are my solutions for number 1. On number 2, I've got my pi over 2 and my 3 pi over 2 that are solutions to my equation. So that's what I'll write up here. Pi over 2, 3 pi over 2. Cool. Thanks, cotangent. You did great. Now, number 3, I'm just listing these numbers right here. So I've got pi over 2, 11 pi over 6, 7 pi over 6. Cool. So really what we're asking you is just a little bit more vocabulary. It's just, can you state an interval solution, and do you know the difference between an interval solution and a general solution? Because there's just a little bit more work to do for a general solution actually than a interval solution. So these would be our answers so far. And like I was saying, I'm going to do the 4th example here just so you all can see one more example, because I know it's kind of a lot. All right, example 4, speed run. Let's do it. We have a quadratic that I don't like it already. It looks quadratic because it's a trinomial, and the first thing is squared. But how do I turn a sine squared into a cosine squared? That's the trick with this one. So we are looking at changing sine squared and replacing it with 1 minus cosine squared. And you might be like, that doesn't make any sense because like this no longer makes it a trinomial, but it does. It is still a trinomial. We do have a little bit more to go to change it back into a usable trinomial, but we're yeah, let's actually do that. So we'll just distribute this, and I almost distributed incorrectly. 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. All right, cool. So I used just in case you missed it, I replaced sine squared x with its Pythagorean identity. Using the Pythagorean identity, 1 equals sine squared x plus cosine squared x. So I shuffled around this identity and I replaced sine squared with 1 minus cosine squared x. So now I'm doing what I've been trained to do. I have to then combine like terms and make it look like a quadratic. Once we have it looking like a quadratic, we should be all right. We should be okay. Oh my gosh, this looks annoying to factor. All right, so we'll try it. We'll use A. We're gonna say A is equal to cosine. So lovely A. So negative 2a squared plus 3a minus 1 equals 0. So now I need to figure out which one of these things is going to be positive and such. So I've got a plus 1 here. I should have a minus 1 right here. And then a minus a right there. We have that set equal to 0, and we are now going to put our cosine x back into this. So 2 cosine x minus 1 is equal to 0, and negative cosine x plus 1 is equal to 0. So my cosine x over here on the left is going to be equal to 1/2, and my cosine x over here is just going to be 1. I'll subtract 1, divide by negative 1, I get a positive 1. Add 1, divide by 2, that's how I get my 1/2. So my x is going to be pi over 3, and I also have a 5 pi over 3. Plus or minus 2 pi n, because that cycles, plus or minus 2 pi n. And then cosine is 1 when my angle is 0. So I have 0 plus or minus 2 pi n. All right, so I hope that was a decent example for you. Just to wrap it up, let's make sure we get the interval solution for this as well. We've got pi over 3, 5 pi over 3, 2 pi, and 0, because 2 pi and 0 are both inside the interval that we're given. So just maybe a little bit of a change there with that one. But that's going to be it for this lesson. Thank you for watching, and I'll see you in class.